Thank you very much for the invitation to this workshop. For me, it's a pleasure and an honor to be the first speaker of this workshop. And well, the pity is that I'm not there, so I'm missing all the fun and all the gossips that usually happen. So after thanking the organizer, I will thank my authors. But first, let me show that because today is post-Halloween, I decided to disguise myself as Alice in Wonderland. So this engraving here on the first slide, it's an engraving from Looking Through the Looking Glass from Lewis Carroll. And you see Alice crossing a mirror. And on one side of the mirror, there is fluid dynamics. On the other side, there is geometry. Okay, so here we have all this complication that we associate to fluid dynamics. And that's the simplification we mentally associate to geometry. This is a representation of the vibration. It's a nice picture by Patrick Masson. And well, in this engraving, by the way, there is a duck there. Okay, you'll see that ducks are involved in this talk too. How are they involved? We're gonna see. Well, first, second people I have to really thank are my collaborators, Robert Cardona, Daniel Peralta Salas, and Francisco Presas. Without them, these works wouldn't exist. I have learned many things of what I'm going to explain from them, including from Robert Cardona, who was my former student, but now I mean, he has been really a gear in this collaboration, and he's now an expert in Turing machines. So what I'm going to explain is contained in these 3 papers, okay? I'm going to, I mean, for me, it was difficult to decide what to keep in the talk and what to keep out the talk. And I hope I did the right decision, but because of course, explaining the details of the proof would be maybe one of these lectures that you are having there of 2 hours with questions and so on. So the motivation comes from nature, right? In nature, fluids often rebel against what's expected. They are indomitable. Indeed, we saw it in the volcanoes in Spain. In La Palma, we have one of these volcanoes, which is like quite unpredictable where the lava will go. And this raises questions, like for instance, are fluids complicated enough to create a fluid computer? And here are 3 pictures. This is Chris Moore from Santa Fe Institute. Here, maybe you don't recognize, but this is Sir Roger Penrose, who wrote this book on Emperor's New Mind, asking these kind of questions almost between mathematics, logic, and philosophy. And here is Terence Tao, who in a way resuscitated this interest for the complications for the existence of fluid computers related to the Navier-Stokes problem. So let's talk about level of complexity. Well, today I will not talk so much about level of complexity. Tomorrow in the talk at 9 a.m. by Daniel Peralta, you'll see that we can attempt to look at different levels of complexity. But let's say complexity, it's a generic, good enough word to say, is the complexity of fluids enough to simulate any Turing machine? And I need one result that we are not used to, which is a result, which is a classical result in logics and in computability theory, which is the halting problem. The beginning of the century, of last century, people were interested in decision problems. Will certain conditions entail a consequence or not? And one of these decision problems was the halting problem, which the question was, can you find a general algorithm to decide if a generic arbitrary computer will finish running, which is the halting state, or continue to run forever? Not a precise one, but a generic one, you know, arbitrary. And Alan Turing proved in 1936 that a general algorithm to solve the halting problem for all possible problems couldn't exist. And he did it, you know, by reaching a contradiction. If you can make this, if such a computer exists, then you can always twist it and change the halting state by no halting state. So, and then you reach a contradiction. And in particular, whenever you have some kind of Turing machines there, and wherever you have the halting problem, you know that it's going to be undecidable. Today, what we're going to do is to associate to a dynamical system a Turing machine. And this dynamical system is going also to be associated to the Euler equation. So we have fluids, we have dynamical systems, and we have Turing machines. But we're going to go there little by little. Do we have H principle? Because this is a workshop of the H principle. We do have H principle. So essentially, this Alice in Wonderland, who today it's me, has to cross the mirror, right, and apply the H principle, where the H principle has been successfully applied. This is the realm, one of the realm is the realm of contact geometry. So we're going to see how to get there. Chronology of the story I'm explaining. These questions, if hydrodynamics is capable of performing computations, goes back to more in 91. And then in 92, there were 29,000 rubber ducks lost in the ocean. Rubber ducks like these ducks. Well, I mean, you can ask, how come I have so many ducks like this at home? I don't know. I do have many of them. Okay, but the question is that that's another question. But 29,000 rubber ducks were lost in the ocean accidentally because there was a storm. And there was, well, here you have a small map. There were some of these ducks were crossing from Hong Kong to Tacoma, and then there was a storm and they were lost. And then, well, there were even advertisements about trying to sell, well, indeed, this is a Seat Toledo that you don't have in the States, but this is a typical European car, where they tried to sell this car by saying that some of these rubber ducks appeared in Scotland. Indeed, they were expected, the 20,000 of them were expected in Scotland, but finally only one of them reached Scotland in 2007, so many, many years later. Well, this looks like a random fact, but we're gonna relate it to the question of undecidability. It's undecidable to know where the ducks will appear. This, you have to think of this as a metaphor, because of course, the ducks move in Euclidean space, and today we're going to twist the Euclidean metric. But tomorrow, we will not. Tomorrow, Daniel will show, and this is here in gray, that we can have an Euclidean construction. But okay, Tao asked about universality of Euler flows in 2017, okay? And then, indeed, we had been working with Daniel Peralta and Robert Cardona on extending a well-known mirror that I will explain between Beltrami vector fields and Revector fields to manifolds to contact manifolds with singularities. These big contact manifolds on which I have been working quite a lot in the last 10 years on bisymplectic manifolds. These are, symplectic structures of manifolds with boundary that explode when they get to the boundary, and the same if they are contact. And then accidentally, I saw this question on Twitter, indeed. Tao doesn't have Twitter, but Tao has a blog, and he posted this question on the blog. And then he was asking about universality. And then I had very clear, we had this picture in mind. So we started to attack with these tools, this problem. And these tools were geometric. And these tools imply the H principle, okay? And this is when we proved in November 2019 that indeed steady Euler flows are universal. I'm going to move this here. And well, this construction that I will firstly describe puts people in analysis not very happy, right? Because we make a construction that indeed we twist the metric on one hand, so it's not the standard metric. And then we go to dimension 17. So there I was, indeed, in November 2019, very happy giving a talk in Zurich about this result. And then people in analysis told me, "What, you went to dimension 17? So the question was clear. Can we improve such a result? Can we go to dimension 3? We couldn't go to dimension 3 using the H principle, but we have been able to make a construction in dimension 3. This is what I will explain. These constructions use this mirror, and this mirror only works for steady solutions of the Euler equation. And what about general solutions, which was the initial question of Terry Tao? Then what we proved last April is that there exists a time-dependent Euler flow, which is Turing complete, but we have to go to high dimension. and dimension is really high. And indeed, this week there is going to be a talk by Francisco Torres de Lizaur, which you shouldn't miss at all. The ones there won't miss. Of course, it's the last one, I think, on Thursday or on Wednesday. And you shouldn't miss it because he's going to explain, give the big tools for this. And then in November, November it's now, we still didn't post on the archive. We will do it this week. We could make a construction which is Euclidean. We decided to keep, secret until tomorrow. So Daniel will explain this tomorrow. And this is an advertisement for his talk. Let's go to basics. I'm going to assume that I'm going to give all proper definitions in, fluids and also in contact geometry at the price of not giving enough details of the proofs. So these are classical Euler equations on R3, okay? This is the classical Euler equations where X is the velocity field of the fluid, and we have an inner pressure, okay? And these are the unknowns of these equations, and we have an evolution following this. This second equation is the divergence. And these equations make sense on R3 with the Euclidean metric, but they also make sense if we change the Euclidean metric by another metric, okay? And indeed, the mnemonics of the equations are the same, and we can write this equation, this is what is sometimes is called the total derivative, okay, as the partial derivative with respect to t, and the covariant derivative, okay, which is compatible with this metric. But essentially, the equations you can write the same, okay, and this divergence also makes sense with a general metric. And these are the equations that we are going to mainly deal with, okay? This corresponds to the movement of incompressible fluids without viscosity. Of course, lava has viscosity. This would be the Navier-Stokes equations. Okay, as geometers, we might be a bit uncomfortable, with, you might prefer to have equations in forms, and indeed forms are key to the proof. So a way to get forms from these equations is to dualize using a volume form, okay, and using a metric, and alpha is the dual to the vector field X, okay, and then the divergence, this equation divergence equal to 0 can be seen as the differential of the contraction of X with mu, okay, and this first equation can be seen as the contraction of the differential of alpha, where alpha is the contraction with the metric, okay, and this is equal to minus the differential of B. That B is what is called the Bernoulli function, okay. Well, sorry, I didn't say something very important. I'm dualizing. I'm going too quick because I'm under pressure to go to the last slide, but important. Now I'm assuming that I'm taking a solution which is steady or stationary. So I'm killing the first term of the former equation, okay? I'm assuming that this is 0. This is what we call a stationary, okay? So from a point of view of analysis, well, maybe stationary solutions are not so interesting. But let's say for us today, the message we want to transmit is that they are complicated enough to encapsulate any problem, any potential dynamic. So in that sense, they are going to be interesting to us. And then the total derivative, in that term, you don't have the dependence on t. This is why you can dualize. You don't have dependence on t on these equations in the dual, sorry. So I'm just looking now at stationary solutions, okay? And Beltrami fields, okay, are one of these stationary solutions, okay? So Beltrami fields satisfy these two conditions, satisfy that the rotational is proportional to the vector field and that the divergence is 0. The rotational makes sense also in these equations, okay? It's the dual to the differential of alpha with these equations here. And examples of Beltrami fields tomorrow, you'll see Beltrami fields more in detail. I'm going a bit quick today. But let's say as geometers, Hopf fields are an important example for us. And while Hopf fields are examples of Beltrami fields, and the ABC flows, so important to study chaos, are also Beltrami fields. Tomorrow, Daniel will also go through these examples. Let's talk about Tau's program for universality of Euler flows. Here we have a picture of Tau working hard. And here we have a picture of matrioskas. I have a student, Anastasia, who is connected here now. And well, if you go to Russia, you get this present, right? You get a present where you have a doll, you open this doll, you have another doll, you have another doll. In a way, this image of Matryoshkas wants to transmit an idea, which is the idea of concentration of energy. Tau's program, Tau had proved long time ago that the average Navier-Stokes present blow up, okay? And the way to do it was to consider some initial conditions. It was a very long paper, but essentially you had some initial conditions which had a lot of symmetry. So his idea is it possible to construct a very complicated initial conditions so that when we plug them in the Navier-Stokes, we have a kind, this is of course, this is not very clear because this has not been done. Can we make them evolve in such a way that we have finite time blow, so that we have this explosion? So a way to program, arbitrary initial conditions would be to use Turing complete fluid flows. And that's why he was asking this question. Related to that, he was asking universality for Euler flows in a way to know if they were representative enough to try to make this kind of construction. So his program of universality and his program to trying to prove the blow up of the Navier-Stokes equations are hand in hand somehow. And he has several papers where he's trying, to show this universality with certain particular conditions, where he's using a very concrete ambient space, a very concrete metric of product type, etc. And he's trying to look at this problem. And his goal is to achieve, this initial datum in such a way that this would make the blow up of the Navier-Stokes. Okay. So when we saw this, we said, this is very cool. Let's try to do this. Okay, of course. So let me explain universality, this idea of universality, with a picture. This is, a random picture, arbitrary picture. I didn't make any particular choice. You come to Barcelona, you take a plane, you arrive here, and that's the first image you see in December. That's a typical day in December, sunny in front of the sea, very nice, perfect, peaceful place. Well, this is not true, but yeah, I was a bit picky choosing this picture. And here we have a picture, standard picture of Paris. Well, it's not very standard to get this guy, here skating as Santa Claus. But let's say these are two pictures, Paris and Barcelona. They are different. But if you go very far, like for instance, if you go to the International Space Station, then you won't see the difference if you are far away enough. And that's a little bit the idea of universality. We want to be able to embed, a certain dynamical system, okay, as an Euler flow at the price of increasing the dimension of the manifold as much as needed. And that's our program, okay? I'm going to assume that nobody knows anything in contact geometry. I know this is false, but here I am yesterday night thinking that this was necessary. I'm going to use the tools I'm going to use is the geometries of forms. And here, well, we are used to symplectic geometry. And I'm going to focus on contact geometry, which is the odd dimensional, let's say, odd dimensional geometry given by a one form that has this condition. The one form satisfies that alpha wedge differential of alpha to the n is different from 0. And this condition is equivalent to non-integrability of the kernel of alpha. If we compare it to Riemannian geometry, then contact geometry doesn't have local invariance, or symplectic geometry. You can always assume, well, not the contact form, but we work with contact structures, not with contact forms, that the contact structure is given by the kernel of this form. And one of the main characters of today is going to be Revector fields. We saw one character was Beltrami fields. These are these steady solutions such that the curl of X is proportional to X. And the other, on the other side of the mirror, the big main character are Revector fields given by these equations. Alpha of R equal to 1, this rescales a little bit the direction. And we assume that the Revector field, okay, is in the kernel of the differential of alpha. and then we rescale it with this condition. This is the Revector field. Of course, we have Hamiltonian dynamics associated to it, and Revector field away is Hamiltonian. Okay, but let's focus just on Revector fields. And if we are, if we are on the standard with the standard contact structure on R3, okay, this is the picture of all these planes, going around. This gives you an image of non-integrability of the kernel. And if you don't like it, you can compute it. Okay, this would be alpha. Then the Revector field here is partial of Z, sorry. And then this is the kernel. And this you can check that you apply Frobenius theorem here, that these two vector fields, okay, the rank is not 2, okay, they are not an involutive distribution, or dually you can compute the differential of alpha, you are in dimension 3, so it's enough to check that alpha wedge the alpha is a volume form, which it is because the computation is simple. Okay, one of the words that I will use is overtwisted in dimension 3. Overtwisted is very easy to make a picture of. In dimension 3, we say a contact structure is overtwisted if you have a two disk, such as the intersection of this is the contact structure, and the intersection with the tangent to the disk has this rule here. In higher dimension, this is the plastic Stufe, which were defined long time ago by Klaus Niederkruger and other people. And well, I mean, I am not an expert who defined it first, but I know Klaus Niederkruger has this plastic Stufe, which attempts to, generalize this overtwisted to higher dimension. And now I'm going to talk about the mirror between Beltrami and Red. So I have to convince you that the example, your favorite example in contact of Revector field is also a Beltrami vector field. So maybe your favorite example is the Hopf vibration that we have here. And well, if this is the case, well, S3, we can look at this, we can look at S3 with this contact structure, and then the Revector field is of this sort. And if you make the computations, this is easy to see that you get the Hopf vibration. And if you are smarter, you use Hopf coordinates, okay, on the sphere. And then you see that the Hopf fields is given by these Hopf coordinates as the partial of phi1 and partial of phi2. And you can check that this is a steady Euler flow Beltrami with respect to the round metric. So we have a vector field that is at the same time Rep, and at the same time it's Beltrami. So it has the two sides. So this is indeed a theorem. We have a magic mirror, and in the post-Halloween day, we are going to be crossing this mirror several times. So how do you look at this mirror? Well, the key point is that, as I said, if you look at these steady Euler equations and you want to think of forms, that the contraction with the metric of the form, it's this one form, is indeed contact. That's the key point. And for that, you use this dual, this is the expression using the language of forms of Beltrami fields. Okay, so here we have a picture of Ednar and Grice, and this mirror is not that converts Ednar and Grice and vice versa, but it converts a problem in fluid dynamics into a problem in geometry. They proved that there is a one-to-one equivalence. Well, this definition of rotational non-singular, it's not important now. It's like it doesn't vanish, and it's absolutely non-singular in the sense that this function is always positive that you have in the definition of Beltrami vector field. And you have this one-to-one correspondence between rotational, non-singular Beltrami vector fields and reparametrized Revector fields. And you can extend this in higher dimensions. You can extend this to this singular contact structure. This is the moment in which we saw this question when we were working with Robert and Daniel. We saw this question on Twitter, and then we decided to go full force. And well, the correspondence works in higher dimensions. So let's look at dimension 3. How do you I'm going to convince you that really this is if I start with Beltrami fields, I get a contact structure. Well, the only thing I need to do in dimension 3 is to check that alpha wedge the alpha, it's a volume form. But the Beltrami equation, if I dualize it, okay, it's written this way. Okay, this is the dual with respect to the volume of the vector field. Okay, and this is the dual, as I said, of the rotational. Okay, and then well, this expression alpha wedge the alpha gets F alpha, F strictly positive, wedge this term here. And if you take some local coordinates, you can check that this is always positive because this is complementary to this. And so this proves, okay, that this alpha is going to be a contact structure. Now we have to chase the Revector field. So when you, well, a good candidate would be the Beltrami vector field, okay? And then, well, you check that the Beltrami vector field is in the kernel of the alpha. You contract, and of course you get 0. But then, is it exactly alpha of x? It's not necessarily 1, okay? Because alpha of x is the metric. It's the, sorry, it's the modulus, because we have defined alpha. We have defined alpha as the contraction of the metric with x. So alpha of x is exactly the norm of this vector. So if the norm of this vector is 1, it's the same. Otherwise, you reparameterize, okay? And then you get exactly a Revector field. And this is how it works. Well, I just proved one of the implications, but it's we can prove the other one, but that's enough. So this magic mirror, indeed, one of the first applications of this magic mirror was by Ender and Rice themselves, in which they were using the case of the sphere of S3 to prove the Weinstein. So they were looking for periodic orbits of Beltrami vector fields on S3. And at that moment, it was already known. I mean, at that moment, when they wrote this paper, the proof of the Weinstein conjecture was not known for general structures. The Weinstein conjecture is a famous conjecture in contact geometry about existence of periodic orbits of this Revector field. And it was proved in dimension 3, but after they proved they wrote this paper of the one-to-one correspondence. But at that moment already it was known for S3. Okay, there was the proof of Hofer. And then they could apply already this Weinstein conjecture to find that you have periodic orbits for Beltrami vector fields. Now we know it works in whenever the Weinstein conjecture holds. And today I want to show an application of this. I mean, we have like, look, the way the applications we are going to do today make you think that you can only apply geometry to fluid dynamics. This is not true. We also have an application of fluid dynamics to geometry, but today I'm not going to talk about it. Today I will present 2 applications. One is the H principle in contact geometry, allows us to prove rep embeddings. And these rep embeddings, because of this one-to-one correspondence between rep and Beltrami, okay, solves the problem, the universality problem for Euler flows, taking as solutions Beltrami fields. Okay, so steady Euler equation. So we will be able to represent any dynamical system in higher dimension as a Beltrami vector field. Okay, and this is thanks to the H principle applied to rep embeddings to prove that if you translate the problem into the language of contact geometry, then the problem is a problem about embedding a vector field as a rep vector field in higher dimensions. Another application that I will explain is this construction of a Turing complete machine in dimension 3. And this uses a part of 2 important ingredients in contact geometry. One is the rep suspension of an area preserving diffeomorphism of the disk that gives you a contact structure. And the second one is using ad hoc Moser's path method to glue contact structures. So this gives the construction of a universal 3-dimensional Turing machine. And what I will not explain, but it's important to know, there are applications of the mirror from the other side, is that you can, for instance, apply genericity properties of eigenfunctions of the Laplacian, which we could say that this is more in fluid dynamics, though we could say it's also geometry, right? Yeah. But this implies by crossing the mirror, this gives you the existence of what we call singular periodic orbits. And today I will not talk about this, but it's another exciting application that I did with a former student of mine, Cedric Oms, and Daniel Peralta-Sanz. Let's insist on the geometrical approach to the question of tau. The question of tau is, can any incompressible vector field be embedded as an Euler flow in higher dimensions. The definition of incompressible would be equivalent to be divergence free, okay? And now we know, thanks to this mirror, that when the Euler vector field is Beltrami, we can use the magic mirror, and we have a problem about, you know, embedding something as a Beltrami vector field is going to be a problem about having a vector field on a certain space, and by increasing the dimension of the ambient space, making this vector field a Revector field. Can we always do this? Well, trick or treat, I would say. We cannot always do it because there is a condition that comes for free if you think a little bit. The first day we were thinking about this, right? If you have this embedding and you want to embed something as a Revector field, then you are going to have an alpha in the ambient space where you are going to have the condition of Revector field for this alpha, which will be a contact structure. So in particular, you'll have this condition here and this condition here. So when you pull back these forms, you need these conditions. Maybe alpha, when you pull it back, is not going to be contact, but indeed, the definition of this, the existence of this alpha, is equivalent to the necessary condition that this describes exactly something that we know, which is geodesical vector fields on a manifold. Geodesical vector fields are vector fields for which you can find a Riemannian metric such that the orbits are geodesics of unit length. And there is a characterization by Hermann Gluck, using the language of forms, which precisely meets what we need. So we have alpha of x equal 1, and the contraction of x with the differential of alpha equals 0. Well, I told you a lie. I told you that we found this the first day. No, it took us a couple of days, and we say, well, we need this condition of geodesical. And well, this condition of geodesical, by the way, it's equivalent to the preservation of a transverse hyperplane distribution. And the first question is this condition sufficient? And the second question is, who cares about geodesical vector fields? Or in other words, how hard is to get a geodesical vector field? I mean, if I take a vector field, this condition seems hard to meet. But you know, Tau is leaving me the possibility to go to the International Space Station, right? To increase the dimension of this manifold. So we have to think if by increasing the dimension of the manifold at this price, we can get a geodesical vector field. So I can answer question 2 immediately, because the suspension of a periodic vector field, if I have a vector field that is T-periodic, its suspension, it's going to be geodesical. And this is a simple computation. If I do the suspension, so I increase 1, the dimension of the manifold, then the suspension of the vector field is going to be like this. I start with a T-periodic vector field. If it's not periodic, okay, then I can embed it, but not in a compact space. Today, I will not deal with this. I made some choices about what I'm explaining. I left something in the basket, so you can go and read the papers. So, of course, this is going to be geodesical because the definition of geodivisibility is the existence of a one form such that these two conditions are met. Okay, and then you take just as one form the differential of theta. This is indeed, by the way, a good example of exercise for an exam in differential geometry. And well, we still have to answer this question. Is this condition sufficient? Well, the first day we were sitting there, the 4 of us I remember, we were sitting in the office of Daniel, you know, thinking like, let's say crazy things, okay? You try to, but immediately we realized that we needed to perturb, right? I mean, in a way, the idea is you have your alpha, now you need to perturb your alpha to make it into contact. So the first idea that came to our mind was to read the paper of Bormann, Eliasberg, and Murphy, which Fran knew by heart. So the inspiration comes from a former result and the methods there of Bormann, Eliasberg, and Murphy in their proof that any almost contact closed manifold is contact. In this, you know, in this interesting, you know, geometrical point of view of looking for obstructions for a manifold to admit a certain geometric structure, there we have contact geometry. And the only condition you have is almost contact. And this almost contact condition you think of it in the following terms. Instead of having a contact form is given by a one form, satisfying this non-integrability condition, then an almost contact structure would be a pair, alpha two form, okay? And these two form, you don't require that is the differential of alpha. So for the ones who were following this nice, that I could only follow online, talk of Yasha last week, or no, 2 weeks ago, I saw it last week, I think it was last week, which it was about exactly the H principle. The idea is this, right? You have a problem where you have the differential of alpha. Now you forget that it's a differential of alpha. You look for a two form. So essentially, an almost contact structure is to have this pair alpha omega, omega non-degenerate. And then the question is, can you integrate this omega to a differential of alpha? If it's three-dimensional, if it's higher dimensional, then the condition, it's the same, but then the condition is alpha wedge omega n, it's positive, okay? And in dimension 3, it turns out that this is automatic. This was indeed proved by Lutz with different methods, of course, because of algebraic topology, okay? Because certain obstructions vanish, okay? Then you look at the proof, well, and they prove more things, of course. Here I gave just a fancy statement, but they prove more things. They find certain overtwisted contact structures for each homotopy class, okay? So, but an important tool is the H principle, and this has been key ingredient for our proof and inspiration. The H principle, the ones who were there already have been following the course of Yasa. The ones who have not been there, maybe not. The philosophy of the H principle is 3 steps. You have a goal. You want to solve an equation, but you can solve the formal equation or linearized equation. So you have a semi-goal. Well, this is usually in life, right? You have a goal and you reach the semi-goal. And then you need a miracle in such a way that the semi-goal is enough to give you the goal, which is that if you can solve the formal equation, then you can construct an homotopy to the form, a formal solution into a genuine or honest solution. For that, you need to be lucky. And well, of course, there are many books written on the H principle. I cannot summarize this in one slide, but I can tell you that what is our H principle scenario? Okay, what we want to find, indeed, I'm going to use the same language of Borman, Eliasberg, and Murphy, where they talk about isocontact embeddings. Okay, here I'm going to talk about isorep embeddings. And the condition is that, okay, I have my initial manifold, remember, is geodesical, not necessarily contact, but I can talk about the kernel of this, the one form associated to the geodesibility condition. Okay, and we say that it's an SREP embedding if you have this condition. If you have this condition, then automatically, because of a former result of Inaba saying that if you have a vector field, he asked himself the question, can this vector field be extended to a Revector field? And the condition he found is that you need that this vector field is transverse to the distribution given by this distribution is going to be a posteriori the contact structure. This distribution is indeed the pullback of this contact structure, okay? And the flow preserves this distribution. And then in view of this, then an isorep embedding indeed gives you a rep embedding. And what is the formal equation? I'm not going to deal with this. I mean, I had a very bad weekend thinking, what should I explain about the H principle? And then I thought, okay, just show a little bit. Okay, if I were there, and maybe it would make sense to make, you know, a longer talk, then it would make sense to explain all the details. But at least I can say what is a formal, what would be the formal object in our world, the formal isorep embedding. Then I'm using here the same language of Eliasberg in his talk, then would be a mapping from the tangent space that covers the initial F. And we have some condition here written with this funny language of the H principle, where you compose and you mean exactly the contra thing, or well, usually you also put the pullback, and you need to impose these two things, these two conditions with H1 and H2, okay? Because you don't know that this F is going to be the differential of a function, so you cannot apply functoriality in a way here. So the definition of formalist or rep embedding, it's pretty ugly. It's this definition. Then our application of the H principle, I say more about it in 2 slides, but in the Overtwisted case, it becomes an application at the end after some gymnastics of the H principle for codimension 0 isocontact embeddings into overtwisted targets. This is a corollary, indeed, in the paper by Borman, Eliasmer, and Murphy, okay? Though we deal with the general case, so it's not that easy. An important thing, as was explained by Yasha in his mini course, is to distinguish what is the difference between any embedding and a formal embedding, okay? Because we want to see if we solve it for formal embeddings, are we solving it for embeddings? In our case, the key observation is that if we have a formal isorep embedding, then the image of what it a posteriori should be, if this is a rep embedding, should be the pullback of the contact structure. The condition is that the image of eta, where eta is the kernel of the geodesimal 1 form, of the geodesimal defined associated to the geodesimal vector field, is an isotropic subbundle. So at the end of the day, you need to talk about Riemannians, okay? And you need to do something that I always do when I work with Frampresas, which is diagram chasing. I don't know how many people are there who have worked with Frampresas, but at some moment in your life, you do diagram chasing because you want to prove that the homotopy of a certain pair that represents the Riemannian is 0, okay? And you do this diagram chasing. This condition is what gives us, indeed, the almost sharp up to 2 embedding that I will mention in 2 slides. This is a little bit a slide that it's a bit incomprehensible, but just to give you the taste of the H principle. I need a dictionary.
Eva, can I ask a question? So why does the image have to be isotropic?
Yeah, it has to be isotropic. Okay, because okay, if you don't impose anything, it could happen also that this image is not even in the kernel of the contact structure. You need
it needs to be contained in the contact distribution, but why does it have to be isotropic?
It has to be isotropic because otherwise we cannot make this work. It has to vanish. I mean, I don't know if you want. I mean, if I was there, I would discuss this. It's a detail. I mean, I could show you more in detail, but it has to vanish. Otherwise, I mean, it's a proof. I mean, it's a theorem of our paper. I don't want to go into this right now because I want to go to explain more things. Okay, I don't know who asked this, but okay, I will postpone this to the end of my talk or to a conversation later this week, maybe. Okay, I need a dictionary to go on because there are 2 concepts that are different. I mean, now I go back to Euler fields, okay? I have a vector field, okay? I want to define, there are 2 different notions here. One is that I want to embed a vector field into an ambient space, okay? In such a way that it's Euler on the ambient space. The first definition is the definition of Eulerizable, in which I don't need to increase the dimension of my space. I have a manifold, okay? And I say it's Eulerizable if there exists a Riemannian metric, okay, compatible with the volume form such that it satisfies this equation. Eulerizable means that this vector field itself, it's a Beltrami field, it's an steady Euler solution, okay, of the Euler equations, okay, without increasing the dimension of the manifold. And then when I want to increase the dimension of the manifold, there are 2 cases. I'm just considering here today the periodic case, because the non-periodic case, the embedding manifold is not compact, okay? So it's a different case. I just choose one. And in the periodic vector field, okay, if I have a time periodic vector field, the condition that I impose is that when I push forward the initial vector field together with the partial of theta, because it's periodic, in the image, okay, if I push forward from M to S1 on the sphere, then this is Euler, it's Euler on this sphere, okay? Okay, and now I want to explain, I mean, I'm 10 minutes at the end of my talk. I'm sorry because I'm going very quickly. I want to explain, to give a hint of the idea of universality theorem. Okay, the dimension of the, I mean, what we could prove is that Euler flows are universal, and the dimension of the ambient space, I will now concentrate on as n on the compact case, okay, is the smallest odd integer between these two, okay? And natural question, are we embedding this on the sphere with the round metric? No, we can guarantee that it's a round metric outside the image of the embedding, but not inside the image of the embedding, because precisely we are using this metric in a way, the H principle is we are using this metric precisely to solve the H principle is perturbing this metric. So we don't have a control on this metric with this construction. So as I said, the proof, the step one is that we use this correspondence between Beltrami flows and Revector fields, okay? And we reduce the problem to studying the universality of these high dimensional Revector fields. And well, as I saw, the red flows are geodesical, but the converse also holds. And we can prove, and this answers the former question one, is this condition sufficient? Is that any geodesical flow is representable? How do we do this? Okay, so, well, if we have a geodesical vector field, then we can embed this on a sphere of this dimension. Here the dimension is tricky, I'm going to explain more. And in such a way that we can put the one form, which is a standard, outside of the image of the embedding, okay? And, okay, how do we do this? First, indeed, we could embed this, you could think that you could embed this in the spherical cotangent bundle, but indeed we need to work a little bit sharper. We need to work with a neighborhood of the zero section, and we need to be able to change the radius of this embedding for our proof to work. But this is a manifold of dimension 2n minus 1, okay? And then we apply Gromov to embed it on the standard sphere of dimension 4 minus 1. If you don't care about the ambient dimension, you end up here, okay? If you care about the ambient dimension, you want to diminish this ambient dimension. The best we could do is to apply the following result. This following result encapsulates all the application of the H principle. We can prove that if we have already a rep embedding, okay, into a contact manifold, then if the dimension of M is bigger than 3, dimension of N plus 2, then we can make this isotopic. In the overtwisted case, we can improve by 2 this embedding, okay, by this dimension of the ambient space. So by applying the H principle, what we do is to kill a necessary dimension of the ambient space. And then to end the proof, remember that we solved question 2, suspensions are always geodesical. Then what we do is to apply this to promote this construction, changing n plus 1. And this is why we end up on a sphere of these dimensions. And then by the contact Beltrami correspondence, we cross the mirror again, okay? And we make this as a steady solution of the Euler equations, okay? Because I have solved this as a rep embedding, then I cross and I have what I have done at the end of the day. I have represented my initial dynamics as a Beltrami vector field on the ambient space, okay? Give me an application related to the program of tau about this. I need to talk about Turing complete Euler flows, and I'm going to give at this point of my talk a very hand-wavy definition. I say that a dynamical system is Turing complete if it can simulate any Turing machine. In other words, if the halting of any Turing machine with a given input is equivalent to a certain bounded trajectory of the field entering a certain open set, okay? So this is the image we have of Turing machines. So what we do in a way is to associate with an encoding, you know, a trajectory, of a flow. Indeed, as an application of our theorem, the first application of this theorem, because Tao had already proved that there was a diffeomorphism, but from this diffeomorphism we can find a vector field, okay, with a time one map, this diffeomorphism on a four torus, okay. Then if we apply this, exactly, we make the promotion of this four with the formula, we get a construction on a 17-dimensional sphere. We can reduce indeed by applying the H principle in Borman, and Murphy. In the overtwisted case, by adding an overtwisted disk, we can do this kind of trick that people often do, that I add an overtwisted disk there, so it's overtwisted, and then I can reduce by 2. Still, I get a sphere of dimension 15, so not dimension 3. Can we do it better? Now I'm 5 minutes to the end of my talk, and I can say, yes, we could do it on a 3-sphere, but then the proof is completely different, okay? As a consequence, by the way, of these constructions implying Turing machines, and as a consequence of the halting problem is undecidable, as the definition of Turing complete is equivalent to the definition that a certain trajectory, okay, is associated to the halting state when it enters this open set, then we get undecidability of fluid particle paths. So there is no algorithm to decide whether a trajectory will enter an open set or not in finite time. This is another manifestation of complexity of fluids, which is different from chaos. So this is quite an interesting consequence of this result of Turing. And now I want to say 2 words about this proof, because I don't have time. By the way, one important thing is that this doesn't give us the finite time blow up of Navier-Stokes. Otherwise, by now you should know. Otherwise, we would have got this $1 million, but we didn't. Okay. And the short answer is no. The long answer is read my paper. Okay. And the long answer is we could plug these as initial solutions and we get a solution that is smooth. So it didn't work. This was the definition of Turing machines, which I'm skipping. But if you don't like this long definition of the tape, this is the one that we are using. You can think about Congruence's way of game of life, which is a cellular automaton, and it's equivalent to think of a Turing machine or a cellular automaton. This is another way to think about Turing machines, like a game with 0 players. Just to finish my talk, and I'm going to skip a construction I'm going to hide in a box. It's a very beautiful construction using dynamical symbolic dynamics to construct a Turing machine in dimension 2, a Turing complete flow. So we use a former construction by Moore, okay, and we improve it, okay. Moore proof that there is a one-to-one correspondence between Turing machines and something which are called generalized shapes that can be represented as application on the Cantor set, on the Cantor square. So what we do is to promote this construction of Moore. Indeed, what we do first is to extend, because this construction is of Moore is just defined on the Cantor square. So what we do is to extend this. Okay, we extend this to an area preserving diffeomorphism of the disk, which is the identity on the boundary. That's what we did. And then what we do is to use this idea of suspension again to promote this area preserving diffeomorphism as the time one map, okay, of a Revector field, okay? And we do this, how do we do this? We do this using the Moser path method to adapt it. So we could prove that if you give me any contact 3 manifold, okay, then you have an area preserving diffeomorphism of the disk. You can always represent the time one map as a Poincare section. Okay, the time one map of the Revector field as you take the time one map of this Revector field. Okay, you can make this conjugate to this area preserving diffeomorphism. That's what we prove. This is a resulting quantized geometry. Yes, but now we cross the mirror. And this, what it does for you is to prove that you have a construction, okay, with a Beltrami field in dimension 3. Why is this Turing complete? Well, this is Turing complete because the initial construction of the disk is Turing complete. It's an extension of a Turing complete construction. And then we are using this suspension, which is a Turing complete construction. In the previous application, where I use the H principle, I was using that the H principle is holonomic, okay, and therefore it's algorithmic. And this is why, let's say, the Turing complete condition survives the H principle in a way. Here in dimension 3, we don't apply the H principle. This is we just apply hands-on Moser-Path method in dimension 3, okay, and then what we have is a construction on a sphere that where the metric outside dense torus is the standard metric. We have another construction that I don't have time to explain that solves the problem with time-dependent Euler vector fields, so answers the question of tau, and it's this theorem that we prove with Robert and Daniel, but I leave this maybe for the questions, where we were using completely different techniques, and the price to pay is that the ambient space, well, you have a representation of any time-dependent Euler vector field in this universality, but price to pay is that the ambient space is pretty big. And what's next? Well, the next thing is the talk by Daniel Peralta Salas, where he will show this construction that we still didn't put on the archive of an Euclidean construction. This would prove, indeed, in particular, that the metaphor of the ducks is a good metaphor, because these ducks live on the Euclidean space. Our construction, these two constructions I have explained today, are not physical in the sense that the metric is arbitrary. We play with this freedom of the metric, with the H principle. Indeed, I mean, when you perturb the contact structure on one side, you are perturbing the metric on the other side. And this gives us the freedom to make our constructions. If we prescribe the metric at the beginning, then we cannot apply the H principle. The tools are completely different, and this will be explained tomorrow by Daniel. Daniel will also have time to talk about other levels of complexity. One, we saw that as a consequence of our theorems, that this shows complexity of Euler flows, because you can represent any dynamics there. But you can ask many questions. What is is the topological entropy always positive? Do you have examples where it's zero? This will be answered tomorrow in the talk of Daniel. And there is a funny game you can play with the Weinstein conjecture and indecidability, because each time you get this, these constructions of Turing machines, you get, as a consequence of the halting problem, this undecidability of the flows, okay? And this is quite rich. This explains, right, this kind of impossibility to predict in nature, okay, the lava, the images that we saw at the beginning of the talk. And with this, I finish my talk. Thank you very much. Sorry for going over time.
Questions? I have a question. So can you explain us the difference between the time-dependent and stationary flow? So is there a different notion of being Turing complete, or am I missing something?
Yeah, thank you very much for your question. This gives me an opportunity to go back to this slide. Yeah, that's a very good question. Here that we need, of course, what is the definition of Turing complete? The definition of Turing complete I was giving too quickly. I'm very sorry. I put too many material, too many things in my talk. Is a definition that we have. I mean, the definition that I have been using up to this point is that we have a flow. We follow the flow, the trajectories of the vector field. We look at this time-independent vector field, and we look at the flow of this as a vector field. If we consider the time-dependent field, then we do a different thing. We consider the vector fields which are divergence-free, okay? And the definition is exactly this one. We say that it's Turing complete if given a Turing machine and an input tape and a finite string, this is not so important, we have an explicit vector field on this infinite dimensional space and an open set here, such that the solution with initial datum are defined for all time and intersect this open set. So the definition is different when we are considering the time independent vector field. And we will see more. I mean, unfortunately, I went over time, but we will see more about this, maybe not tomorrow, but in the talk by Francisco Torres de Lizaur, because he proved, indeed, well, he will not talk about Turing machines, but he was able to embed, indeed, any time-dependent solutions, okay? He was able to embed these time-dependent as Euler equations in these high-dimensional manifolds. What we do, indeed, is apply his theorem, and what we do is to play very different tools. We cannot play the tools of contact geometry. We play the game of polynomial vector fields. There was a construction for people in Grasa and other people in computer science where they use polynomial vector fields, okay? And they were using these polynomial vector fields on the Euclidean space. What we did, it's not like this, I'm simplifying, but we compactify to the sphere, okay? And we regularize this polynomial vector field. And then Torres de Lizaur proved that if you have a polynomial vector field on the sphere, you can embed it as an Euler of equations on a bigger dimensional manifold, a manifold that looks like this. And so it's true that the definition of Turing vector field is different, and the proof, I have used your question to make the proof, to schedule, but not to sketch the proof. Thank you. And well, I mean, I left many things, details that this question that was asked to me, I would be happy, but I would need 1 hour, you know, to make the proof, because let's say the H principle part is like 20 pages of proof, and it's quite delicate. So maybe we can discuss later this week. I don't know who had asked me this question. Was it Cedric de Groot? Was he there? I don't know.
No, Kai, Silvia.
Kai, okay. Yeah, I mean, I cannot reply very quickly because this is a theorem, I mean, that we proved, but I can meet again later in Zoom. I will be happy to discuss this there, but I'm not there. It's like a coffee discussion of 30 minutes.
Any other questions? No, that does not seem to be the case. So thank you again.